Okay, we're recording. Okay, so last time we were talking about partial derivatives, right? And there are some nice things about starting with partial derivatives, but reminder, again, please don't set this as your cornerstone point of view on derivatives. I don't think it's really a good choice for that. Now, of course, it's very, very important, very, very useful, no doubt. The rest of our course is going to be just littered with partial derivatives, of course. But fundamentally, I have a different point of view on what I'd like y'all to think about what a derivative really is. And we might get to that today, but I kind of doubt it. Probably Friday. So how you compute them? We talked about it's kind of for lack of better ideas, I suppose. Let's just turn a multivariable function into a single variable function by holding most of the variables constant. Right? And if you've only got one variable left, then that's a single variable function, and you can just take the usual derivative. And we talked about notation and stuff, but look how easy it is to compute. Again, the only thing that's actually a variable is stuff that's written in terms of what you're taking a derivative with respect to, and all the rest of this stuff is constant. You treat it like a constant. I mean, it comes along for the ride, right? But you don't really have to do anything to it. It just kind of stays there. Okay. All right. And a couple other examples that were, cosmetically surprising, I think, but ultimately same process. It just looks a little weird when you write it down when you have functions in exponents. Okay. All right. So where we left off last time, we were talking about geometric interpretations of the partial derivative. And again, I remind you, you're free to define whatever you want, but then you have to make some explanation of why this is interesting or useful and how it is that you're not just wasting everybody's time. So I need to give some interpretation of what does this do? What does this tell me? What does it look like? Right? So let's remind ourselves what we were doing there. We're going to start off considering a function of two variables, just to kind of get things going. Another quick reminder. The geometric interpretations depend on what kind of a geometric picture have you constructed. And remember, we've got several, right? There's graphs, there's level sets, there's what I like to call the literal interpretation of the function. So if you want to know how to make sense out of your picture, it really depends on how did you make your picture. What kind of a picture is it? So I emphasize what we're going to talk about right now. We're looking at the graph of this function. So we are studying what do partial derivatives look like on graphs. You might say we're starting on exploring the calculus of graphs. Okay. All right. Okay, so that said, we're going to take a partial with respect to y. Partial with respect to y means that y remains a variable. It also means that all of my other variables are no longer variables. They are now constants, right? So x, now a constant. So if I'm interested in particular of finding the partial derivative of this function, making sense out of the partial derivative of this function at this point in the domain, then that value of x is not allowed to change. X has to stay at a, and it's fixed. So what that looks like, of course, is if x is fixed at a, then we are confined to this plane. It's a vertical plane. You might say that it's in the y direction, right? Because it points in the direction, it's, depends on how you want to say it. It's like you're slicing in a direction parallel to the y-axis because x is the variable that's being held constant. Okay. So a reminder, we were looking at a graph of the function. But if we look at a graph of the function and then say I'm only interested in points that are on this gray cross-section plane, then I really don't any longer have the whole graph. Now I have just that slice, just that cross-section. This is a vertical cross-section of that graph in the y direction. How are we doing? Is everybody on board? Everybody remember all this from last time? Okay. Okay. Right. Okay. So, taking a derivative with respect to y, now keeping in mind we're looking at this curve. This is a curve for which the height is the value of the function depending only on y, that being the remaining variable. So height as a function of y, if you think about it, this is in fact a graph of our new single variable function. This is the single variable function. This is the graph of the single variable function whose derivative we want to take. And so when we do get around to then, the next step of, let's see here, taking the derivative with respect to y, we're looking at a graph of a function of y. Taking the derivative means slope of the tangent line. Right, so we've got this cross-section of our graph. Taking the derivative gives us the slope of that tangent line to that curve. And that's therefore our interpretation. Here we go. The partial derivative with respect to y is a slope. And this already we're happy about one thing, right? I mean, we're trying to make sense out of multivariable derivatives. We hope it relates in some convenient, natural, relatable way to single variable derivatives. And good news, our first attempt at a derivative, and it's a slope. Nice, right? So this is already satisfying. More to the point, it's slope of the tangent line. Great. Again, familiar. Slope of the tangent line to the graph. My gosh, it's just exactly like what a single variable derivative is. So it seems, right? Up to this point, all of this verbiage is familiar. Where we do have to be particular, and again, the details matter here. The tangent line to the graph. There's actually lots of tangent lines to the graph. All right, let's go back up to our original picture. There's, in fact, you might even say an entire tangent plane to that graph. So when we say, yeah, it's the slope of the tangent line, which one? There's a bunch of them, right? So in particular, it's slope of the tangent line to the graph, just like single variable calculus. But in particular, it's the slope of the tangent line to the graph in the y direction, in the direction of the variable that you're taking the partial with respect to. What do you say? Everybody happy? Okay. All right. So success. We've made a natural geometric interpretation. Not only is this naturally geometric, it's also familiar. So great news. Happy with this result. You'll notice I only did this for partials with respect to y. I'm going to leave it as a nice exercise, I think, to think about what happens if you take a partial with respect to x. Now, there's a whole process for how to compute x partials. It's a lot like the process for y part. But you're choosing a different variable to be a constant and a different variable to still be a variable. You're going to have a different picture, a different plane, different cross. It's going to look a little different. It's highly analogous. It's going to be morally just like what we did here. Just adapted. And I think it's a really nice exercise to think through in what ways is this question just like the previous, and in what ways is it different? Think it through, draw the pictures, and here's what the answer is you're going to end up with. It's still, slope of the tangent line to the graph. This time just in the x direction. And again, I think this is a nice exercise. Hope you'll take advantage of that idea. Everybody see what I'm talking about here? Okay, now that was graphs. Again, let's not, stick to only graphs. Sometimes we don't want to draw graphs, can't draw graphs, whatever the case may be. So let's suppose that I'm looking, for example, at a function like this one, R3 to R. And you may recall we've already bemoaned the fact that we cannot draw the graph of this function. This is not, I'm going to say it's not possible, and you know what I mean by that. Okay, what we can do is we can draw this, what I like to call literal picture, where we recognize that, okay, well, there's a domain here. Okay, let's draw that domain. There it is. And there's this target here that's R. Okay, let's draw that R. And the action of the function, this function, f, what it does is it takes points out of the domain and it drops them on their images in the target. So again, pretty literal, I think. Whatever you call it, on this picture, how would I interpret a partial derivative? And it's just a different geometric interpretation. Again, though, I'm going to look at the definition of a partial derivative and what does this mean? What is a partial derivative? And well, y is my variable. That means that x and z have to stay constant. That's what a partial derivative is. Partial derivative means all your other variables except for the one are all held constant. So holding x and z constant means that I'm stuck on this line in the domain where x is a and z is c, and y can change, but x and z are stuck and fixed at those values. So I'm stuck on this line. And then I'm going to take the regular derivative. And well, when you're taking the regular derivative, what is the regular derivative? Well, the regular derivative is a relationship between input change and output change. And say it in any of several different ways. I like to think of it as the derivative is the factor that you multiply by the input change to get to the output change. So there you go. That's what partial. I mean, it's not as geometrically satisfying as slope, right? Which is something I could visually see. Very sad. We love graphs because you get these happy answers and these great pictures. But in the absence of a graph and doing the best we can with what we've got, right? The interpretation of a partial derivative in this kind of a picture, in the literal picture, is it's what you multiply by input change to get output change. With the understanding, of course, that you're changing only in the y direction. Yeah.
Can we not graph this as it before dimension?
That's exactly right. Yep. And even on a good day, it's very, very challenging at best. Okay, great. Anybody else? Yes.
Sorry, I'm still a little confused on what the difference between d is and the partial derivative.
The difference between what now? I'm sorry. I understand. Yes. Okay. So this symbol right here, there's some awkward things about mathematical notation. What looks like a numerator here. This thing, partial f, is not a thing. And it's tempting. It looks like a fraction. We write it like a fraction as if this whole thing is actually, this thing divided by this thing. And it's not. That's just not what it is. It's a notation that we use. We represent it with a fraction because it kind of behaves kind of like a fraction in a way, right? But it's not actually a fraction. So when you see this notation, you just have to think, okay, super annoying. It looks like a fraction. It's not a fraction. This is just notation representing this thing called a partial derivative, right? And then what does a partial derivative do? And in this context, the partial derivative is really a single variable derivative of this function. And what do single variable derivatives do? They relate input differentials to output differentials. And these are just plain old regular old differentials like you're familiar with. Is that satisfying?
Yeah.
And again, I apologize for the fact that the math notations are misleading sometimes, and it's very unsettling. Yeah, great question. Anybody else? All right. Okay, what about level sets? So we've seen the calculus of graphs a little bit. We've seen calculus of the literal picture, after a fashion. What can I say about the calculus of level sets? And this is just a small part, by the way. There's much more that we're going to be able to say about calculus of level sets. But for the moment, how would I interpret partial derivatives on a level set picture? Well, let's just kind of think it through here. What is the partial with respect to x? Partial with respect to x means that x is my variable. That means I'm moving in that direction because, after all, y is required to be constant because we're doing an x partial. And as I move in that direction, I know partial derivatives are going to be sort of how much does the function change per unit, how much I move in that direction. On this picture, given the level sets that I've drawn here, how much is the function changing? Where do I see how much the function's changing? And how do I interpret from this picture how much the input changed? Well, how much the function changed is how many lines did you cross? How many contour lines did you cross? How much the input changed is how much distance, in the domain did you cover to accomplish that? And I think you can see here I've gained a bunch of altitude, you might say. I've gone up 2 contour lines. I've gained 200 feet of elevation over very little distance. That's a lot of change per unit input change. So we're going to call that a large partial derivative. Just for comparison purposes, going in the other direction, let's see here, going in the y direction. As I move in the y direction, well, look at that. I've got to travel a much greater distance in the domain to gain that same 200 feet of elevation. And so we have a relatively small partial with respect to y. Now, this isn't quantitative exactly. I can't look at this picture and see, that looks like about, 6 or what have you, right? Because I don't have any labels as to what are the values of the function on these various level sets, and I also don't have any labels of how far or which distances in the x and y direction. So I don't get that crisp, satisfying, slope, right, like you do with graphs. But you can kind of make some sense out of what's going on here. And just for a real world, relatability thing, imagine again that these are contour lines on a hiking map, right? And you're trying to decide how to build your road. Should you build your road in exactly the x direction? Oh my gosh, you're basically going straight uphill. No one's going to be able to drive up that road. Maybe someone in like some sort of Jeep or off-road 4-wheel with a winch, something like that, right? But if you instead just kind of mostly follow the contour lines, but maybe just kind of cut somewhat in the uphill direction, but mostly follow the contour lines, then it's not as steep. And then regular old cars can make it up there. And here, just for fun, here's an actual example. So this is, by the way, if you ever get a chance and if you're looking for excitement, this is a truly scary road to drive on. This goes to the top of Mount Evans in Colorado, which I've done several times, once as a grown-up where I was actually driving. It's scary, right? It's very scary because you're so high up. It goes up to 14,000 feet. And furthermore, the drop-offs, and you can't really tell, again, there's no sort of perspective here. It's hard to get a perspective. But if you look at these contour lines, and you look at, this is 14,000 right there. And let's see here, where is 13,000? I think this is 13,000 right there. So that is 1,000 feet of vertical difference. And you can see this here is 500 feet horizontally. So that's about a 45 degree. That's about like this. So as you're driving along, that's what's on your left. Don't fall. Don't drive off the side. And then there's the little matter of also being, since you're at 14,000 feet, your brain doesn't work right. and your ability to perceive and your reaction times highly lowered. It's a legitimately scary experience. Anyway. But notice what the road does, though. The road doesn't just go from here, just right up there to the top. That'd be ridiculous. Too hard, right? Notice that the road basically follows contour lines. Not exactly, right? The contour lines are kind of more like this, but it's mostly following the contour lines and just gaining a little bit of elevation at a time. And then they do this thing called switchbacks that, again, allows you to mostly follow the contour lines, but then also generally kind of go in the same direction. So anyway, I think this is pretty relatable in terms of making sense out of how much function is changing with respect to how you're following contour lines, and how it kind of stands to reason that this is shallower. Right, and this is steeper. What do you think? Okay. All right. So, we're going to work up now to a different kind of a derivative. It's going to take us a bit to get there. I'm going to start with a question. I'm going to start with the question of how do you find what we'll call a linear approximation to a function. A quick little side note, the functions that we're going to write down, technically they're not linear. Y'all just came out of a linear algebra class. Y'all hopefully are very attuned to the word linear and what linear means, and linear means something very precise. And these functions, tragically, are not linear. They're linear-ish in a way that they are computed with something that is linear, and I'll comment on that in a minute, but just full disclosure, I feel the need to point out technically these are not. But anyway, what is a linear approximation? And I want to remind you from Calc 1, we have this function that I'm sure you all have seen. This is called the linear approximation. It's a degree 1 polynomial, right? The graph is a line. Now, what makes it the linear approximation to the function? And again, my purpose here is not to review. My purpose is to pick out key aspects of this that we can then generalize to our current situation, right? What is it that makes this a linear approximation? We're looking at a function that has the same value and the same derivative, same first derivative, as my original function. There's various different ways that you can think about linear approximations. This is the one that I'm going to go with because I think it's most useful for what we're about to do. It's a function that has the same value and the same first derivative as the function that I'm approximating. Okay. And easily confirmed, by the way. I'm sure you all have all done this in a single variable calculus class, that this function indeed has these properties. And if you haven't done that calculation before, it's something everybody should do once in their lives, and I encourage you to take a few minutes. And works out pretty straightforwardly. Okay, so this is what I'm gonna pull out of this and apply in our new multivariable context. When we're looking for a linear approximation to a multivariable function, we're going to be looking for a degree 1 polynomial that has the same value and the same first derivative as the function we're interested in. So here's what that looks like. Same value. Same first derivatives. Wait a minute. We don't really have a single just the derivative for multivariable functions. We have partial derivatives, but they're all kind of first derivatives, if you will. And so I'm going to require that all of the partial derivatives of this of a linear approximation should equal the corresponding partial derivatives of the function I'm approximating. So this is what I'm going to say is this is how you would extend single variable requirement of a linear approximation to a multivariable requirement. of a linear approximation. It's just same thing, just in appropriate to our new context. What do you think? So far, everybody okay? Now again, this is something that you can hunt through and play with and try to find, but here's what the answer is going to be. This is the function that agrees with f in value and partial derivatives at the given point A. And again, this is just a plug and chug and confirm, right? In the same way that this, you can directly confirm, has those properties. Well, likewise, this thing down here, you can directly compute and confirm that, sure enough, it has all of these properties. And again, I think it's a healthy exercise. If you've already done this, then just do the analogous confirmation, the analogous calculations on this function here to confirm these. If you get stuck on this, by the way, there are a couple of sticky wickets. You do have to think through, wait a second, what is a partial derivative? Don't forget that when you're taking a partial derivative, only that one variable is a variable. Everything else is a constant. You treat it like a constant, right? So if you do get stuck on this, come to office hours. We'll talk about it. I'll be very happy to show you how this works. But give it a try on your own first. I think it's a healthy exercise. Okay. So then real quick, a little notational thing. If you look at the way we've got this written, there's a couple of things about this that I don't like. One is it's kind of long, right? Because most of the way across the page, that's undesirable. Another thing I don't like about it, it's got the ... in it. That it's uncomfortable, right, to have that written down. So there's a way around this, and that is to observe that a lot of what's going on here, there's a kind of a pattern. So in particular, notice here, I've got the coordinates of the x vector being subtracted. I'm subtracting then the coordinates of the a vector. And really, that's just, that's the vector x minus a. All this together is the vector x minus a. It's the coordinates of the vector x minus a. And then I look at these factors, and I don't really recognize, I mean, they're partial derivatives, yeah, right. But as a vector, is this something that I recognize? It's not. But I can say, you know what, it sure would be nice to give that thing a name. Let's call that a vector, because if I make this choice, I'm just going to take all the partial derivatives and put them together to make a vector. Because if I do, this looks just like a dot product. And I like it when cool, convenient stuff like that works out. This whole thing then starts to look just like, that dot product right there. So this making this choice to take all the partial derivatives, assemble them into a vector. This is called the gradient, for which we use this notation. Making that choice, making that definition allows me to rewrite an kind of undesirable looking equation into a much more compact, much more convenient, elegant little formula. What do you think? Everybody okay? All right. So, yes, question.
How do you read a triangle?
Yeah, that's a great question. We're actually, for the moment, I'm going to say you'd read this as gradient of G. Yeah. The time is going to come later in the course where we're going to actually pronounce this different. We're going to actually do different things with this symbol. It's morally the same, but kind of different. And I don't want to. It's way off in the future. So just as a foreshadowing thing, let me say eventually we will call this something else, just for terminological reasons. But for right now, gradient of G. Yeah, great question. Okay. Yeah. Oh yes.
So this only helps us rotationally, right? It doesn't simplify.
Well, for the moment, we're doing this just for notational convenience. That's right. Now, some of you may already know some multivariable calculus, and you may know that this thing called the gradient, it's actually really cool in a couple of ways. But I don't want to get ahead of myself. We can't justify those yet. So for the moment, it's just a notational convenience. Absolutely. Yep. You might say it's a notational convenience, or now that I've written the equation of the linear approximation in this form, then it is a participant. It's a major participant in the formula for a linear approximation. Yeah, right. Okay, so here's a quick example. Got a multivariable function here. Let's write down the linear approximation of this function. Let's say at that point 1, 2. Now, of course, you get a different linear approximation depending on where you compute the linear approximation. Okay. All right. Well, I'm going to need to know the gradient. The gradient is made up of a bunch of partial derivatives. I'm going to need to compute the partial derivatives here. So here we go. We compute the partial derivatives. That's just partial derivatives a la what we started with today. Don't forget, when you're taking partials, the other variables are to be treated as constants. Right? So you get these partials right here. Yeah. Okay. Notice further that I have to evaluate the gradient at the point in question, right? So I've got to plug in these values, x equals 1, y equals 2. I've got to plug those numbers in to there, and therefore the evaluated gradient is the vector 2, 4. How we doing? Is that good? Okay. So with that done, then I'm kind of in business. I mean, I know technically I gotta take my point and I gotta plug that in to here, and I gotta evaluate what the function is at that. Okay, fine. So that gives you 5, as it turns out, and so that's 5. The gradient is 2, 4. And then I dot with x minus a, and again, x minus a, don't forget that x is the vector with coordinates x, y, and a is the vector whose coordinates were given, and that's 1, 2. So, plug and chug, there you go. That's the linear approximation. Okay. Now, you can, I suppose, you could kind of multiply all this out and collect terms, in which case, if you do, then you get this as the linear approximation. In a way, that's simpler, but there's also something undesirable about this. Having written the linear approximation like this, then all of what's going on is kind of now concealed in how I've simplified things. So, really, unless I were going to need to be punching out values of this function, and I need the arithmetic as simplified as possible. I mean, really, this is kind of better because I can see the value of the function, I can see the gradient, and I can see what I'm doing with the gradient, namely dotting it with the input displacement. Okay. All right, so most of the time, in fact, I don't feel the need to do that simplification. Okay, so great. Here's a shortcoming with what we've done. We've only considered real valued functions. Now, yes, we've considered multivariable real valued functions, but still we've only done real valued, and so, okay, what if we have a vector valued function? And this is going to be a little bit harder to write down, but we're going to take the exact same approach, morally, it's the same fundamental idea. We're going to be looking for, and we'll get into the details in a second. We're going to be looking, though, for a function that mimics f in value and in the various partial derivatives. Now, what partial derivatives are there? Well, there are partial derivatives with respect to, all of the different input values, x1 through xn. So all the different xj's, right? We're taking partials with respect to all of those inputs. But when you do, you're taking partial derivatives of a vector-valued function, which means you're going to be taking partials of the various coordinates of those output vectors, all the various output coordinates, which is a whole different list, right? So the outputs are F1 through Fm, appropriate to this being an M dimensional target. All right, so there's not just a list. I mean, I guess you'd say back in this real valued multivariable case, I just have a 1 through n kind of list of partial derivatives that I need to deal with. Right now, over here, I have both I and j are going to be ranging. There's a kind of a whole array of different partial derivatives that I need to check actually work out the way that they're supposed to. Okay. So, again, I'm not going to derive the answer. I'm just going to show you the answer. And it's much better to confirm than it is to derive. Less work. And so here's the answer. It's kind of beautiful. The answer honestly looks an awful lot like the previous answer. The previous answer, recall, was this. It was value plus, mystery expression, times the input change, the input displacement. Which, by the way, again, same exact thing that we had up here. Value plus this thing times input change. So we've got a pattern going here, right? Single variable, real valued multivariable, vector valued multivariable. It's the same pattern in the answer. And the only weird different thing about this answer is that this is it's not a scalar, it's not even a vector, it's a matrix. And this is just what works. Yes?
Would we still call that the gradient?
No, it's not so the gradient, the word gradient means specifically what I've got here. It means a vector. You really only talk about the gradient of a real valued function. So this as a construction only for real valued functions, and it is always a vector. That's right. So in this multivariable context, we have a different name. I'm temporarily. Anyway, I made a point of not writing it down. But why don't I call this? I'm going to call this the derivative matrix because it has all the partial derivatives. It's the matrix that has all the partial derivatives in it. You might even call it the partial derivative matrix, I guess. But there's another name for this that I don't want to give away too soon for dramatic purposes. So this anyway is the matrix that makes that formula work. This is another healthy exercise, right? And it's going to be a little tedious, right? Because there's so many of elements of that. So maybe make yourself a matrix, or make yourself a function that has let's say 3 inputs and 2 outputs, something like that, right? And write down what this matrix looks like in general for 3 input variables, 2 output values. And you can write down the matrix and write down this form, and then to confirm that this always works, right? For those values of n and m, and there's going to be 6 terms, but I think that's something that's still reasonable to deal with. Okay. What do you think? Everybody see how there's a pattern? Oh yeah, question.
What does WRT stand for again?
With respect to. Yeah, that's just one of my own little abbreviations. Yeah. With respect to. Okay. Heads up about one thing. It is important that you assemble this matrix as noted, namely that the first column is all with respect to the first input variable. It's got to be a column. It's not arbitrary. Given that linear algebra works the way it does, given the standard conventions of linear algebra, the choice of this matrix in the calculus has to follow that convention, and we end up needing the input variables, the variables that you're taking partials with respect to need to correspond to columns. And then notice that the output variables, the output coordinates, correspond to rows. So heads up, it's easy, so easy to accidentally transpose this. And if you transpose it, then it's wildly wrong. It's really importantly, it's not going to work, right? So heads up and be careful about that little seeming micro detail, but it's very important. Okay, so another example, and this is just plugging and chugging really, but here's a multivariable vector valued function. And I can talk about what would happen if I look near this point, 1, 2, and what is the linear approximation. And, well, here's the matrix of partials. That's just partial derivatives. Again, make sure you can do that. You got to think, there's, calculations to be done. Make sure you're good with that. Then you got to plug in the point to get the matrix of partials at that point. And that goes there. And what do you do with it? Well, you matrix multiply by the displacement, input displacement, x minus a. Add the value of the function. The value of the function, well, you're going to have to compute the value of the function there. Again, you're going to have to take your point and plug in to compute the value of the function at a. But it's all just plugging in and following the form. Everybody happy with that? All right. Okay, a couple of quick observations. Neat fact. I kind of already said this in the first part in some sense. If you were to look at a column of this matrix of partials, right, the matrix of partial derivatives, well, it's all, every element in that column is a partial with respect to x1. They're all partials with respect to x1 of the coordinates of f. So in fact, then, if you think about it, assembled as a vector, that column is the partial of the vector-valued function f itself. So it's kind of a neat observation. I mean, it's not much of an observation, but this is literally what would happen if you were to take the partial with respect to x1 of the vector-valued function in question. And then each column then is a partial of f with respect to a different input variable. Okay, the rows, now a slightly different observation. The rows, I claim each of the rows is a gradient. And let's think that through. We'll go back up here to the formula. Here's my formula. Let's look at the first row arbitrarily. Well, notice we're always, everywhere in that row, we're taking partials of f1. As previously noted. Let me say that a little bit differently then. All of these elements are partials of f1, and furthermore, this is all of the partials of f1. All of the partials of a real valued function. All of the partials of a real valued function. Where have I seen that before? Oh yeah, here it is. It's literally the gradient. That's the definition of the gradient. All of the partials of that real valued function. So so just kind of a neat observation. The rows of the derivative matrix are gradients of the coordinate functions, the component functions, if you want to call them. Okay. All right. Next, again, I've already kind of apologized for this. The linear approximation function is not linear. It's not a linear transformation. Easily confirmed, by the way. One of the requirements of a linear transformation is that 0 has to go to 0, and that's clearly not the case here. Right? You can just plug in x equals 0, you don't get 0, so it's not. But why do we call it linear? df, being as it is a matrix, is a linear transformation. df, the thing, the primary object, the thing that's doing all the heavy lifting, in this being a linear approximation. That thing is linear. And so you might say that we call it a linear approximation because we're using a linear tool to approximate. So a slight abuse of the term, but anyway, that's how people talk. Okay. All right. Now you might have noticed that everything we've done so far has been algebraic. Right? I defined linear approximations algebraically. I didn't say the word tangent plane anywhere. You might have noticed. Conspicuously absent. Because I want to take an algebraic point of view on linear approximations. Okay. So, next though, what is a tangent plane? Well, y'all know what tangent planes look like. The big point I want to make here is that tangent planes are graphs. They are graphs of the linear approximation. So, if we have a function f, recall there's this construction called the graph of f. The graph of f is, again, a certain curve that I generate by a certain construction, a certain process applied to the function f. So, light green, little f is a algebraic object. It's a function. In dark green here, we have a generated picture generated by, again, a particular kind of arbitrary construction that makes this curve, not to be conflated with the function itself. Okay, likewise now, we've got our linear approximation. Here's our linear approximation. How would I put the linear approximation on this picture? Well, if I'm looking at the graph of f, maybe I should entertain what is the graph of the tangent line of the linear approximation, and the graph of that linear approximation is what we call the tangent line. Okay, so again, that seems like a minor distinction, but you don't be sure not to conflate linear approximation with tangent line, because one's an algebraic object, one's a geometric object, and again, it's different. It's an important distinction. But they are, of course, very closely related. One's the graph of the other. So, same deal with multivariable functions. And the tangent plane is the graph of this linear approximation. And I say it's a tangent plane because, again, if we have a function of two variables, we're looking at a surface. There's lots of tangent lines to a surface, but there is a unique tangent plane. And again, it's the graph of the linear approximation, just like in the single variable, analogous to the single variable case. Everybody good? Okay. Oh, yes.
Could you go over again then what the tangent line is, if the tangent plane is the graph?
Well, they're both. So they're both graph of the linear approximation. The difference is the sort of the context. So in the initial case we were looking at a function of one variable. When you have a single variable function, right, then there's only one variable, and so you get a tangent line. Here we have two variables, and so you're going to get a plane. It's just geometrically different picture. Yeah. Okay. Yes.
So do we always use the gradient operator for the tangent plane, or could we also use like the derivative matrix?
That's a great question. I am only going to define tangent planes for, you'll notice here, real valued functions. You can define it just gets real weird because if you think about it, the simplest case that we could possibly have of a multivariable vector valued function would have four variables, and the graph is, I can't even begin to draw it. So even in this case, this is the simplest possible scenario of a multivariable function. Two, just barely multiple. right? 2 inputs, only 1 output, and it's already a 3-dimensional picture that I'm already kind of stretching my artistic abilities to be able to draw. Yeah, so we can't draw tangent planes for vector valued functions, but you can define them. It's still the graph. It's just that it's going to be, it would be like a 3-dimensional plane in a 7-dimensional space, and we're not going to, not in Math 219. That's right. Okay. Good. You know what? We're out of time, and this is a good stopping point anyway, so we'll draw the line right there. Y'all have a great Wednesday. See you later. Oh, and of course, as usual, if you came in after I did attendance, please make sure to come up and make sure that I click you down for present.